Exoplanet transit physics represents one of the most powerful methods for detecting and characterizing planets beyond our solar system. This technique relies on detecting the slight dimming of starlight when an exoplanet passes between its host star and an observer on Earth. During a transit event, an exoplanet blocks a small fraction of the starlight, creating a characteristic dip in the star's brightness that can be measured with high-precision photometry. This seemingly simple phenomenon allows astronomers to determine a wealth of information about distant worlds, including their size, orbital parameters, and even atmospheric composition. The mathematical relationships that describe transit events, combined with advanced observational techniques, have revolutionized our understanding of planetary systems throughout the galaxy, revealing an incredible diversity of worlds and challenging many of our preconceptions about planetary formation and evolution. The transit method detects the passage of a planet in front of its host star, an event known as a transit. When exoplanets pass in front of their host star as seen from Earth, a portion of the starlight is blocked out, and a decrease in the photon flux is measured. This method only works for star-planet systems that have orbits aligned in such a way that, as seen from Earth, the planet travels between us and the star. The basic geometry involves a dark, opaque disk, the planet, moving across the face of a bright disk, the star, temporarily reducing the total amount of light received by distant observers. The alignment requirement means that only a small fraction of existing planetary systems can be detected using this method, as the planet's orbital plane must be nearly edge-on as viewed from our perspective. The sensitivity of the transit method depends critically on the relative sizes of the planet and star. Jupiter creates a transit depth of approximately 1% when passing in front of a sun-like star, while Earth would create a much smaller signal of about 0.08%. These small changes in brightness require extremely precise photometric measurements, explaining why space-based observatories like NASA's Kepler mission have been so crucial to the success of the transit method. The remarkable precision of modern observations allows astronomers to detect planets much smaller than Jupiter, including Earth-sized worlds, by measuring these minute changes in stellar brightness over time. The scale of these measurements is impressive. The entire span of a typical light curve graph showing transits often represents variations within just 1% of the total brightness of the star. The transit depth provides direct information about the size of the exoplanet relative to its host star. To first order, assuming the stellar disk is of uniform brightness and neglecting any flux from the planet, the ratio of the observed change in flux to that of the stellar flux can be expressed as d RP-R2, where RP and R are the planetary and stellar radii respectively. This elegant relationship allows astronomers to directly calculate the radius of an exoplanet when the star's radius is known. For example, a transit depth of 0.6% for a star with twice the Sun's radius would indicate a planet with approximately 1.5 Jupiter radii. The transit depth measurement is one of the most straightforward parameters to extract from a light curve and provides essential information about the physical nature of the detected planet. When combined with mass measurements obtained through other methods, such as radial velocity observations, the planet's radius determination allows astronomers to calculate its density. This critical parameter provides insights into the planet's composition and internal structure, helping to distinguish between rocky planets, gas giants, and various intermediate types. The main advantage of the transit method in this regard is that the size of the planet can be determined directly from the light curve, something not possible with most other exoplanet detection techniques. The planets that have been studied by both transit and radial velocity methods are by far the best characterized of all known exoplanets. The total transit duration is heavily dependent on the impact parameter, which is defined as the sky-projected distance between the center of the stellar disk and the center of the planetary disk at conjunction. This parameter ranges from 0 for a central transit to 1 for a grazing transit, and significantly affects the light curve's shape and duration. Assuming a circular orbit, the impact parameter can be mathematically expressed and determined by fitting transit models to observational data. A transit with an impact parameter of b max 0 crossing directly over the stellar center, will have the longest possible duration for a given orbital configuration, while transits with higher impact parameters have shorter durations and longer ingress-egress times. The impact parameter relates directly to the orbital inclination of the planet relative to our line of sight. Radial velocity observations provide information about the minimum mass of an exoplanet, assuming the stellar mass is known. However, to constrain the actual mass of an exoplanet, the orbital inclination must be measured, which can be done by fitting an analytical transit light curve to the data. A transiting exoplanet with a high impact parameter will have a shorter transit duration, a shallower transit depth, and longer ingress and egress times compared to a more central transit. These variations in the light curve shape allow astronomers to precisely determine the orbital geometry of the planetary system. The total transit duration, defined as the time during which any part of the planet obscures the disk of the star, contains valuable information about the orbital properties of the exoplanet. Using geometric principles, the transit duration can be expressed mathematically in terms of the stellar and planetary radii, the impact parameter, and the orbital parameters of the planet. For a circular orbit, the length the planet travels across the disk of the star can be calculated using Pythagoras' theorem as 2 rp2 b2, where b is the impact parameter. The planet's orbital velocity then determines how long it takes to traverse this distance. The transit duration, combined with the orbital period, allows astronomers to calculate the planet's semi-major axis relative to the stellar radius. This critical parameter helps place the planet in context within its solar system and provides information about potential habitability. The duration of the transit is also affected by the eccentricity of the orbit. Planets on eccentric orbits may have transit durations that differ from those expected for circular orbits. By precisely measuring multiple transits and their durations, astronomers can detect these subtle effects and characterize the orbital dynamics of the planetary system with remarkable precision. The transit method makes it possible to study the atmosphere of the transiting planet, providing insights impossible to obtain through most other observational techniques. When the planet transits the star, light from the star passes through the upper atmosphere of the planet. By studying the high-resolution stellar spectrum carefully during and outside of transit, astronomers can detect elements and molecules present in the planet's atmosphere. Different atmospheric constituents absorb light at specific wavelengths, creating a transmission spectrum that serves as a fingerprint of the atmosphere's composition. This technique, known as transmission spectroscopy, has been used to detect various molecules in exoplanet atmospheres, including water vapor, methane, carbon dioxide, and even potential biomarkers. The apparent size of the planet varies slightly with wavelength due to the wavelength-dependent absorption of its atmosphere, causing the transit depth to change when observed in different wavelength bands. Space-based observatories are particularly valuable for this type of analysis, as they can observe at infrared wavelengths, where many important molecular features are prominent, and avoid the interference of Earth's atmosphere. These observations provide crucial insights into the chemical composition, temperature structure, and even potential habitability of distant worlds. The transit timing variation, TTV method, examines whether transits occur with strict periodicity or if there are variations in their timing. These variations can reveal the presence of additional non-transiting planets in the system through their gravitational influence on the transiting planet. If a transiting planet is the only significant mass in orbit around its star, its transits should occur at perfectly regular intervals. However, gravitational interactions with other planets in the system can cause slight variations in the timing of these transits, providing an extremely sensitive method of detecting additional planets with masses comparable to Earth's. It is easier to detect transit timing variations if planets have relatively close orbits, and when at least one of the planets is more massive, causing the orbital period of a less massive planet to be more perturbed. The first significant detection of a non-transiting planet using TTV was carried out with NASA's Kepler Space Telescope, which revealed the presence of Kepler-19c through its gravitational influence on the transiting planet Kepler-19b. These observations demonstrated TTVs with an amplitude of 5 minutes and a period of about 300 days, showcasing the remarkable precision achievable with modern transit timing measurements. In circumbinary planets, variations of transit timing are mainly caused by the orbital motion of the stars, rather than by gravitational perturbations from other planets. When a planet passes behind its star as seen from Earth, a phenomenon known as a secondary eclipse or occultation occurs. During this event, any light reflected or emitted by the planet is temporarily blocked, causing another small dip in the combined light from the system. These secondary eclipse observations provide unique opportunities to study the thermal properties and reflectivity, albedo, of exoplanets. When detected in the infrared, secondary eclipses allow astronomers to measure the thermal emission of the planet at different wavelengths and reconstruct the structure of its atmosphere. Secondary eclipses are particularly informative for hot Jupiters, which can reach temperatures over 1000 K and emit significant infrared radiation. By measuring the depth of the secondary eclipse at different wavelengths, astronomers can construct a thermal emission spectrum of the planet, revealing information about its temperature structure, energy distribution, and even atmospheric circulation patterns. These observations have revealed details about heat redistribution from the day to night sides of tidally locked planets and have provided evidence for temperature inversions in some planetary atmospheres. The combination of primary transit and secondary eclipse observations provides a comprehensive view of an exoplanet's physical and atmospheric properties. The physics of exoplanet transits represents one of the most powerful frameworks for exploring planetary systems beyond our solar system. The elegant mathematical relationships that describe transit events allow astronomers to extract a wealth of information from seemingly simple light curves. From basic physical properties like radius and orbital parameters to sophisticated analyses of atmospheric composition and thermal characteristics, transit observations have revolutionized our understanding of exoplanets. The geometric principles underlying the transit method are straightforward, yet their application has revealed an astonishing diversity of planetary systems that challenge our theories of planetary formation and evolution. As observational technologies continue to advance, the transit method will likely play an increasingly important role in the search for potentially habitable worlds, and perhaps even signs of extraterrestrial life. The combination of transit observations with other techniques, such as radial velocity measurements, provides the most complete picture of exoplanetary systems currently available to astronomers. Future space missions and ground-based observatories will push the boundaries of transit detection sensitivity, potentially enabling the detailed characterization of Earth-like planets around nearby stars. The remarkable physics of transit phenomena, coupled with increasingly sophisticated observational and analytical techniques, ensures that this method will remain at the forefront of exoplanet science for decades to come.